and welcome you all. ꯑꯗꯨꯒ ꯃꯩꯇꯩ ꯀꯩꯅꯣ ꯉꯥꯛꯇꯅꯦ ꯃꯅꯤꯄꯨꯔꯗ ꯅꯨꯡꯉꯥꯏꯖꯔꯒꯦ ꯁꯤꯒꯤ ꯇꯣꯛꯁꯦ ꯑꯩꯈꯣꯏꯒꯤ ꯀꯩꯅꯣ ꯖꯅꯋꯥꯔꯤꯒꯤ ꯑꯣꯏꯅ ꯑꯍꯥꯟꯕꯗꯤ ꯑꯣꯏꯕ ꯑꯗꯨꯒ ꯄꯤꯝꯁꯥꯒꯤ ꯁꯨꯝ ꯑꯩꯈꯣꯏꯅ ꯃꯟꯊꯂꯤ ꯔꯤꯒꯨꯂꯔꯂꯤ ꯁꯤꯜꯂꯛꯄꯗ 28 ꯁꯨꯕ ꯇꯣꯛ ꯍꯥꯏꯇꯥꯔꯦ. So we are very delighted to have with us ꯌꯥꯝꯅ ꯁ꯭ꯄꯦꯁꯦꯜ ꯑꯣꯏꯕ ꯑꯦꯛꯁꯄꯔꯠ ꯑꯦꯁꯇꯔꯣꯏꯗꯇ ꯊꯕꯛ ꯇꯧꯕꯤꯕ ꯑꯗꯨꯒ ꯌꯥꯝꯅ ꯑꯦꯁꯇꯔꯣꯏꯗꯁꯤꯁꯨ ꯌꯥꯝ ꯏꯝꯄꯣꯔꯇꯦꯟ ꯑꯣꯏꯕ ꯍꯥꯏꯇꯥꯔꯦ. ꯑꯩꯈꯣꯏꯒꯤ ꯑꯔꯊꯀꯤꯗꯁꯨ ꯊ꯭ꯔꯦꯠ ꯑꯣꯏꯕ ꯑꯩꯈꯣꯏꯒꯤ ꯀꯩꯅꯣ ꯑꯣꯏꯕ ꯑꯦꯟ ꯗꯦꯟ ꯐ꯭ꯌꯨꯆꯔꯗꯁꯨ ꯑꯩꯈꯣꯏꯒꯤ ꯅꯦꯆꯔꯦꯜ ꯔꯤꯁꯣꯔꯁꯀꯤ ꯄꯣꯇꯦꯟꯁꯤꯌꯦꯜ ꯌꯥꯝ ꯂꯩꯕ ꯀꯩꯅꯣꯅꯦꯕ ꯑꯩꯈꯣꯏꯒꯤ ꯑꯗꯨꯒꯨꯝꯕ ꯃꯤꯁꯇꯔꯤꯌꯁ ꯑꯣꯏꯕ ꯑꯩꯈꯣꯏꯒꯤ ꯁꯣꯂꯔ ꯁꯤꯁꯇꯦꯝꯗ ꯂꯩꯕ ꯀꯩꯅꯣꯁꯤꯗ ꯌꯥꯝ ꯊꯕꯛ ꯐꯖꯅ taubiba akhoi expert tamo Dr. Guneshwar Thangjam is with us today to share his valuable knowledge, and I hope this talk will be very interesting. And then thank you all, and we have the title of his talk is Planetary Exploration, an Overview and a Potential Asteroid Mission. So Aduna, with this to start with, I would like to request Tamo Romi to give a brief introduction of our speaker to our audience today.
Before I start with today's speaker's brief introduction, I would like to request our President, Oda Khaidem Ranjan Kumar Singh, to give a welcome address.
Okay, thank you, Romi. Thank you, Kogen, and a very warm welcome to Dr. Guneshwar Thangjam. ꯑꯩꯈꯣꯏꯒꯤ ꯄꯤꯝꯁꯥꯒꯤ ꯆꯠꯊꯔꯛꯄ ꯄꯔꯤꯡ ꯅꯥꯏꯕ ꯑꯩꯈꯣꯏꯒꯤ ꯁꯥꯏꯟꯁ ꯑꯦꯟ ꯑꯦꯀꯥꯗꯃꯤꯛ ꯇꯣꯛ ꯁꯦꯔꯤꯁ ꯉꯁꯤꯒꯤ 19 ꯁꯨꯕ ꯑꯩꯈꯣꯏꯒꯤ ꯇꯣꯛ ꯁꯦꯔꯤꯁ ꯍꯥꯏꯒꯗꯔꯦ ꯖꯅꯋꯥꯔꯤꯒꯤ 2026ꯀꯤ ꯑꯣꯏꯅ ꯑꯍꯥꯟꯕ ꯇꯣꯛ ꯁꯦꯔꯤꯁꯅꯤ. ꯍꯥꯏꯔꯤꯕ ꯇꯣꯛ ꯁꯦꯔꯤꯁ ꯑꯁꯤꯒꯤꯗꯃꯛꯇ ꯑꯩꯈꯣꯏ ꯉꯁꯤ ꯄꯥꯔꯇꯤꯁꯤꯄꯦꯠ ꯇꯧꯕꯤꯔꯤꯕ ꯑꯩꯈꯣꯏꯒꯤ ꯄꯤꯝꯁꯥꯒꯤ ꯔꯦꯁꯄꯦꯛꯇꯦꯠ ꯃꯦꯝꯕꯔ ꯃꯌꯥꯝ ꯌꯥꯎꯕꯤꯔꯤ. ꯑꯁꯤꯒꯤ ꯃꯊꯛꯇ ꯑꯩꯈꯣꯏ ꯌꯥꯝꯅ ꯁꯤꯅꯤꯌꯔ ꯑꯣꯏꯕ ꯑꯣꯖꯥ ꯑꯗꯨꯁꯨ ꯑꯩꯈꯣꯏ ꯀꯩꯅꯣ ꯄ꯭ꯔꯖꯦꯟ ꯑꯣꯏꯕꯤꯔꯤ ꯉꯁꯤ. ꯑꯩꯈꯣꯏ ꯈꯨꯗꯤꯡꯃꯛꯀꯤ ꯕꯤꯍꯥꯐꯇꯒꯤ ꯗꯥꯛꯇꯔ ꯒꯨꯅꯦꯁꯋꯔꯕꯨꯁꯨ ꯑꯃꯨꯛꯀ ꯍꯟꯅ ꯑꯩꯈꯣꯏ ꯇꯔꯥꯝꯅ ꯑꯣꯛꯆꯔꯤ. Not only this, I have seen many other participants during today's talk series who are not from PIMSA, and a very warm welcome to all of you also. And I am very sure the exploration of the space and though is extended to subject of physics is a very interesting subject nowadays. And basically, as you know that the space is infinite, and though I'm a physics student, I was a physics student, I have a very limited knowledge. But as we look up at the sky in the night or in the daytime, we see a vast sky. And in fact, our space is multiple, you can say millions or billion times what we see when we look up at the sky. And it is a very interesting phenomenon. Until today, there are still many mysteries are going on. We are not able to explain with the available physics and other physical sciences, whatever it is. So people who take keen interest in this particular subject is a very challenging thing, because a lot of theoretical works, at the same time, a lot of experimental works are required to be carried out. And when we say experimental works, a lot of the what is called the experimental setups, which are very costly, and only some few countries have this type of facilities in today's world. And you'll be happy that India also, particularly initially the Tata Institute of Fundamental Research, they are the pioneer in doing this subject, and now it is many other the what is called prominent institute also coming up in India, which are taking up very keen interest in this subject. And not only that, from the government of India, particularly from the Department of Atomic Energy, this department is taking up very keen interest in this area, and there is a separate budgetary support is there from the department, and this is going to be a very challenging and a very interesting field, which is still carrying on. So I will take much time, and today's talk from Dr. Guneshwar, it will be very interesting. I'm very sure, and we will be able to absorb at least some of the things which are still going on there, whatever the mysteries that is happening in our universe or what we call space. So now I pass on to Dr. Romi to, for the further, uh, to proceed the further about today's talk. Okay, over to you, Dr. Romi, please.
Thank you, Azhar Ranjan. Uh, it is my privilege and honor to have this chance of introducing uh, one of the globally renowned scientists in the field of planetary science, and which happens to be a very close friend and a colleague of mine, Dr. Thangjam, Guneshwar Singh Thangjam. So, Dr. Guneshwar Thangjam is currently working as a faculty in the School of Earth and Planetary Sciences, National Institute of Science Education and Research, NISA Bhubaneswar, which is an institute under the Department of Atomic Energy, Government of India. Dr. Thangjam completed his PhD from Max Planck Institute for Solar System Research, Göttingen, Germany, in planetary remote sensing and reflectance spectroscopy, studying the asteroid Vesta's surface composition and geology using NASA's Dawn framing camera and visible and infrared spectrometer data. After completing his PhD, he continued his postdoc in the same institute in the area of planetary exploration, where he studied asteroid carest surface composition and geology using the same Dawn mission spectral data, and also contributed in Dawn FC payload and mission planning. He was working in as a GRF in the Space Applications Center, SAC, Ahmedabad, in the area of lunar morphological and spectral analysis using India's Chandrayaan-1 data. He completed his master's in geology in Bundelkhand University, Jhansi, UP, and also worked as a JRF in the same institute studying landslide and neotectonic along the main boundary thrust in the Himalayan regions of Uttarakhand. He has achieved many significant achievements during his tenure as a researcher as well as an academician. And one of the most significant contribution, which is of global importance, which I would like to mention here, and which came into the limelight of the Indian scientific community globally, is that in the honor of his significant contribution to planetary science, particularly his work, which he did during his PhD with the data from NASA's Dawn mission to Vesta, the International Astronomical Union, IAU, officially designated the previously known asteroid, which is named 1981 EF14, with his name as Asteroid Thangjam, which is also referred to as Asteroid 11806 Thangjam, bringing pride to the scientific community. And this asteroid Thangjam orbits the Sun between Mars and Jupiter, and this recognition was officially given by the IAU in 2017. Dr. Thangjam's current research interest and work includes planetary surface composition, hyperspectral data processing, as well as instrumentation development, geochemistry of planetary analogs of early magmatic volcanic origin like cometites, and anorthosites. So with this astonishing biodata, brief biodata, I now request our today's eminent speaker to proceed with his talk. Thank you.
ꯑꯍꯥꯟꯕꯃꯛꯇꯗ ꯑꯩꯒꯤ friend Romi ꯑꯗꯨꯒ ꯑꯩꯈꯣꯏꯒꯤ ꯑꯣꯖꯥ ꯃꯌꯥꯝ ꯑꯩ ꯈꯨꯔꯨꯝꯖꯔꯤ ꯑꯗꯨꯗꯨꯒ ꯑꯩꯒꯤ ꯇꯣꯛꯁꯤꯗ ꯁꯣꯏꯕ ꯈꯣꯠꯄ ꯑꯗꯒꯤ ꯀꯩꯅꯣ ꯇꯧꯕ ꯌꯥꯎꯔꯒꯁꯨ ꯑꯣꯖꯥ ꯍꯣꯏ ꯑꯗꯒꯤ ꯃꯌꯥꯝꯅ ꯉꯥꯛꯄꯤꯒꯅꯤꯅ ꯈꯟꯖꯩ ꯑꯗꯨꯒ ꯑꯩ ꯁꯤꯌꯔ ꯇꯧꯔꯒꯦ
Slide share tꯧꯕꯤꯌꯨ.
Sharing content. Okay. Choose that you want to share.
aduga ai marak thana tamo keno na Guneshwar na keno slide ki share tawdringaida mayam da sum any if you have any questions or if you want to interact with the speaker at the end of this talk you can ask questions or even you can use the chat box to put down your question and we'll read out to him and you can have the answer simtang ai keno to hoge to yeah please tamo
Slide share ubirabra.
Udri, amtaga share tꯧ.
Started sharing content. Okay. Skip share content. Roaming aside, this alone share token.
Share option that chango.
Share option change and
Windows chango. Windows option the logo.
Next. Okay. Sorry. Yes, here. So share. Share tawra bro.
Ure anangi kano do slide to capture. Yeah. Yeah. Full mode to capture.
Okay.
Now it's visible. Yeah.
Okay. Rome English to dong kana tawra na tragana dum Manipuri da.
Yeah.
yeah,
Animal
it's okay,
mix
Tamo,
also
it's your, you can use the bilingual whatever.
Yes.
It's in the view, yeah, that's right.
Okay. So the talk is actually organized in 3 parts. The first part, I just want to cover the planetary science and also how the surface is important in this planetary science. And then the second part, how the surface properties, mainly referring to the chemical properties, the composition, how reflectance spectroscopy can be used as a technique or as a tool, and also as a part of my research. And then in the third part, just want to share one of the ideas that I shared in the planetary community in India, and also with some of the colleagues in ISRO. So here the background I choose the pale blue dot. So I think this is known to everyone, and the talk is actually arranged in such a way that it can be interactive. And also when I talked to Romy, he also suggested me that students are also participate. So in that regard, I thought if some of the takeaways can be taken, and it can open room for discussion, and that's why I designed the slides in that way. So here the meaning of my slide here is to show or start with the Earth in the context of planetary science, is that when we talk about, for example, geology, say my main work is planetary geology. So either it is Earth's geology or it's a planetary geology, Moon, Mars, and so on. Everything starts from the Earth, our home, and then everything ends there. So, and if we look, if the Earth is actually the so-called a planet in a very far world. For example, nowadays exoplanetary science is actually booming, and as you know, when we say exoplanets, then it is actually in the other star systems. So here, this is a kind of an example, Earth referring to a distant planet, and how it looks like, and then how it can be actually studied, or can have a perception, and it gives us lots of philosophical ideas, just not the science ideas. So with this, I'm coming to the the planetary processes. And when we talk about planetary processes, this is summary from a book, Planetary Surface Processes by J. Mellows. So he's one of the pioneers. Anyways, so here this very beautifully summarizes the important processes, and the ones in the red, these are actually quite important ones. So for example, tectonics, volcanism, impact cratering, and yeah, and since the audience is actually from different backgrounds and subjects, I will try to cover some or definitions or basic parts, and hopefully uh, everyone can follow the slides. So yeah, the red ones, it tells us the main so-called primary or important processes, while the blue ones, for example, refers to some not that relevant or not that significant in terms of planetary science. And that's because when we talk about moon, for example, it's also called a kind of a dry planet, and in that case, weathering and then the surface fluids is actually not playing a role, as we do see in case of Mars and Earth. But what I mean to say is that when we look any of the planets, it may be Earth or it may be any of the asteroids or comets or exoplanet, but the moment we see that planet from the surface itself, we are able to see and think what kind of processes might have actually underwent in its history. And that's how we can infer to its main processes just peering through that surface. And for example, even here, the dense atmosphere and so on, and then whether and some of the planets may be still very active. And I will also come to that some of the examples. So, regardless of whatever the processes that might be happening in, or maybe in an unknown planet, the surface and the processes plays a very important role. So let's start from Earth. As I said, everything starts from here. So when we do see the surface, and when we do a map from this perspective, for example, it actually represents on a global scale, what do we see? The volcanic units, the ocean floor, and then let's say the plate boundary, different types, and then different types of structural features and so on. So it itself tells us that this planet, so-called Earth, is actually a very active one. Active in the sense, geologically, the dynamic processes internally going on, and as a result, the processes in coupling with the atmosphere, that's also going on. So with this, if we look this kind of similar surface mapping to other planetary objects, for example, either it may be Mercury and the moon and so on, then what do we see is that in contradiction to the Earth, so for example, in Earth, we have so many volcanic units or structural features or morphology, but if we move to any of the planetary objects, most commonly, what do we see is actually the so-called these impact craters. And the frequency of these impact craters and also the whatever the morphology we see on the surface, it tells us what processes might be happened or still happening, or even what will happen. And then so one of the difference what we do see here is that all these three, the moon, Mercury and Mars, somehow looks quite similar, though there are differences. But these Venus, it gives a different perspective, and it tells exactly the same, that yes, Venus is different from when we talk about moon, Mercury and Mars. And that's because Venus remains one of the very interesting planet or object, and still very, very poorly understood in terms of its processes and so on. So that tells us that Venus is or in the very recent past, it was very, very active. And with this, we can also infer to the time scale or what processes might have happened starting from the very early formation. So for example, these are actually the plots that the surface manifestations or surface features that we have seen. And now, after analyzing in detail all these features of the surface, so-called the surface features, now it comes to a timeline. So starting from this 4.5, the very formation, then we do see that, okay, these gray zones, these are the events in the time period that are uncertain, that remains uncertain, and it is obvious. And then these ones, major volcanism time scales, and we can see for Earth, it still goes on. And Venus, well, this is from a publication in 2009, if I remember correctly. So that's why the understanding for Venus is actually very poorly constrained, and it is actually very of interest that though others activities in case of Mars and Mercury are known fairly, maybe up to 1.5 billion years. By the way, this is actually in billion years till the present time. And Venus, 500 million years or so before that, what happened and what extent of activity that remains very, very poorly characterized. And now it is hypothesized or widely accepted that Venus might be still active. So this volcanic, this color is supposed to continue with a question mark till the present time. Yeah. So this tells the importance of this, let's say, the surface processes and the surface features. Then, as I said, one of the very most common features is impact crater. And here I'm just sharing impact craters in different scales. And this is an example from Arizona, the meteor crater. I think it's around 20 kilometers in diameter. Sorry, 20, yeah, I don't remember exactly. So, and we can see the rims and so on. And there is a very nice kind of history recognizing the impact craters, because in the earlier times, very similar to the science contradictions and so on. There was a time or a period that so-called these impact craters, this is actually impact craters or volcanic features. So there were so many debates and so on, and then now it is actually established that yes, this is an impact crater. That is because of incoming projectile from the asteroid belt or so, and that's how we do see. And then in India, Lonar Lake, for example, that's also one of the very well-known impact crater in India. And this is one of the examples in one of the icy moons. And here, what we do see is the impact craters in different scales. And here we can see 1 kilometer scale, 5 kilometer, 50 kilometer, and yeah, and then different types of impact craters. So I'm not going into those details. And then also these tells us that it's not just in the visible scales to our eye, but also in the micro scale. So for example, this is from 1 micrometer scale, and that's what, these impact craters gives us lots of scientific information in different scales depending on our interest of the problem. And it tells us one of the evolution of these craters. So very so-called juvenile or younger to a very older one, and then it tells us the as a kind of cloak, where the statistics of the, or let's say the distribution or the frequency of these so-called impact craters can be used as a marker to estimate how old or young is the surface, and so-called a technique, planetary crater counting. And it simply counts the craters per kilometer square or given space, and then there are functions, so-called how many craters are produced and then erased over time, and then it has been proven with the return lunar samples, and that's how, using those algorithms, it allows to date the surface, just like the radio S dating of geological samples, not exactly in that way. And it is understandable that this is a remote sensing technique and it has uncertainties and so on. So then volcanism. So when we talk about volcanism, so these are different, let's say, the way the volcanoes or the volcanic features are actually visible for moon. So very small ones we can see here. And then, sorry, I forgot to include the scale. And this is Olympus Mons. This is one of the, this is actually the tallest, or let's say we can say the largest volcanic feature in the entire solar system. And this one is from Venus, and this is one from Mauna Kea, Hawaii. One thing about Venus is that, and these are also from Venus, and here just showing the profile of different volcanic features, and then the extent, and Olympus Mons, Mauna Kea, and then this Mat Mons, for example, this one that is not that tall, or the elevation is just only around 10 kilometer or around 9 kilometers, but we can see the extent, and this is actually in 1,000 kilometer of spatial unit. And so volcanism actually plays a very important role after this impact crater. Now, when we talk about the surface features, one of the clues is about so-called tectonism. And in the planetary context or in the geological context, on Earth, plate tectonics, that is a very well-known one. And when I say tectonism, it does not necessarily mean plate tectonics, but it means tectonic features. And for example, these kind of understanding are not well established. Not well established in the sense this is not that proven when I say about Venus, for example. So this is actually just yeah, comparing with the tectonics or tectonism on moon, Earth, and then the Venus. And so-called blob tectonics is given the name. And then this is for the Earth. We know that plate tectonics causing the convergence, divergence of the plates, and then these deformations. And in this blob tectonics, so that understanding is still, yeah, people come in the community are debating, and then whether this kind of tectonics is actually existing, or is it similar to, or at some point of time was there a plate tectonics, and so on. And then this is for one of the icy moons. Yeah, so and this is for the I think this is for the moon. I should have labeled it. And this is from the one of the icy moons in Jupiter. So here we can see lots of structural features, and these are called linears, and this is actually also shown here. So this is 50 kilometers in scale, and then we can imagine that how big these structures are. And when we see these kind of features, then the next thing that is actually asked is that what causes this kind of features or phenomena. And then okay, plate tectonics, yeah, in case of Earth. And then for other planetary objects, okay, most probably this kind of stagnant lid convection. But yeah, when it comes to Venus, and then this Europa, then things are different. And then it is widely accepted some form of tectonism may be still going on. Yeah, so this one I can actually skip. Different types of internal processes, for example, this crust, lithosphere, and an astronosphere. And then for example, this IO. This is IO is still the activity going on, and then it is also compared with so-called the comatite eruption time of Earth. Means the very it is actually suggested as the in the present time the very comparing to the very early stage of these magmatic eruptions. And then Venus, Mars, and the Moon and Mercury. So so the idea is that the surface manifestations or the features in terms of the deformations, it tells us a very important clue to the internal processes. And then now I'm coming to the surface, to the surface as to this interior. For example, in the earlier slide also we have seen, but here is coming to mainly the chemical properties. And I'm not going into the details, but from the elements to the minerals. And so in geology, as you know, minerals are actually aggregates of the inorganic crystals crystallized from the compatible so-called elements, or the groups of elements. And then yeah, I will come into these details. And then these minerals form the different rock types, and then these rock types then form whatever the planetary objects in our solar system or beyond. And then so this is a simple sketch, not and simplified in such a way that it can be representative. And we have seen here different layering, and then this is referring to the Earth, and with different depth profiles, and then what kind of dominant mineral compositions, and also the structure simplified in such a way that these representative minerals tells in terms of their physical and chemical properties. So when I say different physical and chemical properties, we can also see in this nice diagram from the core to the mantle, and then the surface. So the elemental compositions, and then if we interpret these elemental compositions in terms of their minerals compatible minerals that will be forming or stable in that particular temperature and pressure, then we can refer these ones, for example this perovskite, and then other. And then also when it comes to the and also I want to tell here that as we go down, then even for Earth there are lots of debates, and then the problems whether these perovskite is actually in these particular let's say depths and so on, and then other associates and so on. Yeah. But we have a very good or fair understanding despite of that, and for example here olivine and so on, and yeah. All right, so and then this shows the seismic or the velocity profiles, and then these kind of velocity profiles are also used combining with this mineral physics. And then it tells us the potential or the plausible compositions, and then the physical properties. So as I said, there is a very good understanding, fair understanding of the Earth, though still there are problems. But when it comes to planetary science, then many things are actually not known, and that's why the study has to combine with lots of observations, and then also so-called numerical modeling, and then also the experimental stuff. So now I will come to the from the surface. We'll come to I will try to simplify, and then how it made possible to study. And before that, when we talk about any surface, this is with reference to the Earth, so-called this Earth geology or mineral. And what we know is that the major component of the mineral system is actually this silicate, and then this silicate, as we know, this is just a tetrahedra, and the silicon, and then the oxygen, the 4 oxygen. But when it these silicate, it forms a complex anion, and then that anion, in order to balance with so-called the cations, then it comes with what kind of cations, and then what kind of structure, crystal structure, and then it comes to, okay, then let's say 6 or 5 types of these silicates, and they are given different names, and then on Earth varieties of silicate minerals are available. Here it represents a kind of a family. So for example here, an easy example, olivine. And when we say olivine, so the chemical formula is 2 magnesium and then 1 silicate, but it comes not necessarily with magnesium, but it is actually a magnesium and iron, because these are 2 divalent cations, and then most of the olivines are with Mg2 plus and Fe2 plus, but there are also let's say manganese or nickel, and then so on. So in the reality, it's more than the simplified chemical compositions. Yeah, so here, coming to the planetary perspective, most of the planetary objects are actually of igneous origin, or well, I will come into that. So in that case, the olivine and the pyroxene, these are actually very common ones. For example, if I talk about moon, but it depends on whether the planetary object has not actually undergone the melting process. Then, for example, these kind of silicates, so-called seed silicates, are actually plays a very important role, and also this kind of feldspar and then so on. So yeah, so depending on this nature, we can actually study the surface compositions, and when we talk about non-silicates, these are also important, very important ones. For example, carbonates, sulfates, oxides, and sulfides. So what I want to bring to the second part after this is that when when we want to study the surface compositions with the known chemical formulas and then the structures, then the reflectance spectroscopy allows us to study. So so reflectance spectroscopy, as we know, this is the study of the reflected light or the flux, but it's a kind of interdisciplinary approach where the images acquired through the spectrometer, by the spectrometer, has to be processed in different steps, given the different natures of illumination geometry, and then the noise or the spectral response, and then correcting with the surface nature. When I say surface nature, in the nature, it is actually a very complex pattern of so-called roughness, and roughness, it can be in the micro scale or in the meter or in the kilometer scale, and that has to be accounted. So data processing. So yeah, so here one of the images just from this spectrometer from this NASA down visible infrared. So we can see these vertical stripes and so on. So these has to be processed in at least 3 or 4 steps. Yeah, and then it also involves lots of laboratory analysis. So for example, these are the facilities available at NICER, and then I just took the snapshots. One of the samples of, yeah, this is a comatiite sample, and then these are meteorites, and these are the pellets that we prepared. So this is FTIR, and this one is Raman, and then this one is yeah, the ACM. Yeah, so so when we have the spectra from the lab of our reference samples or the analog, then we compare those different lab and then the observations, and then also look, let's say, the geochemical properties, what kind of elemental composition or what kind of oxide compositions are there, and then how it can be forming a different what kind of minerals, and then what kind of rocks and so on. So coming to the reflectance spectroscopy, so as I said, mainly the reflected component is what acquired by the instrument, but but over time, what we are, or in the reality, what we are getting is also the emitting, the emitted component. So yeah, depending on wavelength, what window we are actually using. So for example, here it's showing 0.4 visible to the near infrared, around 5 micrometer, and then when we see different absorption, so these are actually the absorption features, and then we look what energy is equivalent to these spectral features, and then what actually it can cause. So and then we also look comparison to the library spectra. So this is very well established, the vibrational process and the crystal field effects. Yeah, just as an example to show, from around 0.4 to 2.5 micrometer, and this narrow window is actually the one mainly used in planetary surface compositional studies, including the Earth. And it's a very good understanding, and this kind of understanding is actually based on the electromagnetic nature, or let's say how the light or the photon is actually interacting. And in that case, we have to understand what is actually the physics going on, and then that physical property, how it is actually interacting with the crystal chemistry of those particular minerals. So these remote sensing studies is a combination, or is on the shoulders of the physics and the chemistry of those materials. So I'm not going into these details. It just shows different temperatures in different response, and then accordingly uh, what kind of material property could be, so that kind of inferences we can make. And this is one of the very well-known example from Peters et al. 2009 science paper, so-called the discovery of water on moon, but it's actually OH oblique H2O. So-called water is actually in the hydration form, and still not well established. Either it's a molecular kind of water, or is a hydroxyl, or a kind of very fine layer of water ice, though they are actually quite well understanding or acceptance in the community that it is likely thin flakes of coatings, or but yeah, the origin, either it's actually from the moon itself, or from the micrometeorite interactions. So here it represents different laboratory samples of so-called minerals. So I'm not going into the details of what kind of minerals and so on. But different minerals have their own signatures, and these signatures is actually made possible to interpret by these data, or these observations is because of the, as I said, the nature, the physics and the chemistry behind it. And I have a slide, I will come into that. And this is actually from Chandrayaan-1 and from the moon. So this one, 3 micrometer absorption. So 3 micrometer absorption, for example, here. So the intensity is actually higher in the polar regions, and one of the areas shows higher response, and this is interpreted as the evidence or the presence of this OH vibrational feature. So as I said, the detections or the spectral features, they pop up because of the crystal chemistry. And here are the crystal chemistry. For example, this one, for example, olivine distortions in the M2 site and M1 site. And then, for example, this one is pyroxene, and we can see that pyroxene, which is actually these two are actually pyroxenes. So it is very nice absorption features around 1000 nanometer, and then this 2000 nanometer, and this is made possible because of this crystal structure or the nature, and then the transitions in this. These are actually the d orbitals, the 5 d orbitals, how they are actually transitioned in this, and then so the spectral features. This is yeah. So in order to understand the spectral nature, we have to understand the crystal chemistry, and also how those wavelengths or those photons interact with these crystal structures, and then what kind of energy transitions happened, and that energy transition is equivalent to this energy indicated in this wavelength scale. So this is just a slide to show the different methodological to characterize the spectral features. So we just try to look the absorption, so-called absorption band center or absorption band minima, and it shows that that kind of absorption feature here is actually indicative of what kind of cation, and this is mainly actually Fe2 plus cation in this case, and this Fe2 plus is actually, if it is olivine for example, then what kind of crystal structure, either maybe this Fe2 or this Fe2 plus either in the M1 side or M2 side, and then how much of energy transition, and then their crystal coordinations and so on. So that actually when we look that particular wavelength position, and also what kind of let's say intensity from this continuum, then it tells us the amount as well. But when we want to estimate the amount, then we have to consider other factors, that what kind of combinations of minerals, and then what kind of physical properties might be affecting, for example, grain size and so on. Now coming to the third part, this is, I have taken moon as an example. So when we talk about the planetary perspective, moon and the Mars, the main focus or the reachability for India, and Venus mission is actually now approved, and most probably I think yeah, 2027, probably 2000, yeah. Last time I attended one of the conferences, and then I also met Tamo Raghu. Yeah, so so for India, now moon is done in this case, reached, and then Mars, and then the Venus will be there. Then after this, what? So then obviously we know that, okay, this is time for small body exploration. Small body means asteroids and the comets. And in the history of planetary exploration, either it's from NASA or ESA, asteroids are usually explored because they are reachable, and because the technology is also very important one apart from the science interest. So that's why I just thought that I will share this, and then I already shared this idea with my colleagues in ISRO. Yeah, so if we look to moon, for example, because moon is the one that started so-called the planetary exploration, starting from the Galileo's telescopic observation, and then that's how the names are given, that low length or mare, for example, and then high length and so on. So we see that there were so many landings starting from this 1960 or 70s, and then 1969 the Apollo 11 landing is actually a kind of a breakthrough, or I also have a slide on that. So one of the I think it was told that the most technological advancement in the history of mankind. Anyways, so the idea is that so many missions, especially the landing ones, happened, and then this shows different sites. And recently China is actually very advanced, and you can see that the India and China started almost the journey in the same times, let's say 2007, 8, I think, yeah. So India's Chandrayaan-3, that's a huge success. Chandrayaan-2 as well, though the deployment of the lander and the rover was actually turned out to be a crash landing. Nevertheless, it's a very nice and historic achievement. And China, for example, that's also very historic achievements, and then they're also moving ahead. So, for example, they have written the samples, sample return missions, 2020 and 2024, 2 times. And this 2024, that's a fantastic one, because they have landed on the other side of the moon, so-called the far side of the moon, and that is actually technologically very challenging, and that is actually decades of preparation because the telecommunication and then that kind of technology is really, really challenging. So yeah, I just took this example for moon, because as I said, many nations are now actually popping up, and then also in full gear. And it's also one of the questions that we can ask to ourselves, that in 1969, for example, if we look these Apollo missions, it started in 1969. Here only shows Apollo 11, but Apollo different Apollo missions were also there, the previous Apollo missions, but this is the one that we know. And so it stopped in 1972. And then you see it's 2025, 2026, and then this kind of missions is not coming back. So it's a kind of question. And you also may have heard that whether this Apollo landing was a hoax, or is it real, and so on. Anyways, so it's coming back, and that's why, for example, this Artemis program is just kind of a reflection to the Apollo, and then the China, the space agency, and also this Japanese, and then yeah, and they are even planning for bigger ones from moon as a kind of interplanetary medium for further planetary explorations. Okay, I will just plug. Yeah, and then this is also of concern, or an advancement, that moon mining and and space tourism from many startups. These are also going on, and we can see from these Artemis mission programs, and then Chinese space programs, and also Indian space programs. It's a kind of space race at the present time. Yeah, so I have covered this Artemis. So as I said, this Apollo and Artemis, just twins. And then Artemis is actually trying to bring back the Apollo era with vigor mission concepts. And this is as a glimpse for the Chinese moon mission. And as I said, they have different programs. Okay, so this Chang'e 6, they have already done the samples, and then you can see the sample capsules, and then their rover, and then so they have shown their technological advancements actually. And then this is one of the thin sections. Anyways, so yeah, this is the concept for the lunar far side. They have to in the L2 orbit, for the telecommunication, it has been already sent there, and then through this they made it possible to land on the far side, and then also bringing sample from this lunar far side to the Earth. So it's a technologically, yeah, very advancement. Now coming to the Asteroid mission. Sorry. Yeah, sorry. So here I'm just sharing, and I will quickly move these slides. So here it shows the potential targets from the perspective of NASA's exploration program, and I took these pictures or the images from JPL website, and then we can see that yeah, this represents the Jupiter's orbit, and then the asteroid belts, how this so-called the asteroid belt pops up, and then the different orbits of the inner solar system. So the largest asteroids here I'm just showing Ceres, the largest one, 1,000 kilometer approximately in diameter, and then the second largest Vesta, and this has been explored already by this NASA down mission, and then different small asteroids that has been explored so far, and then these two are actually they remained to be explored, and so my idea was a mission to explore this fourth largest asteroid. Yeah, and then what kind of science interesting problems, and then what kind of technological feasibility, or in terms of the instruments. So in this case, this is how, using remote sensing spectroscopy, how the solar system, especially the asteroids and the comets, are studied. And the asteroids in the solar system, they are actually classified in such a way that how the surface spectroscopy or the reflectance means. And here, for example, this is approximately 2 micrometer here, 2.5. So we can see that 1 micrometer feature and 2 micrometer feature, and then if this feature means, then then it's mainly pyroxene, for example, and that's why it has given the name V-type asteroids. And if it is actually featureless, then actually this is mainly oxides, because oxides usually iron oxide kind of compositions, usually they don't show up, and then E-type, and then if it is and then S-type, M-type, C-type, and so on. And these overall represents what kind of, let's say, compositions. When I say here B-type, S-type, and so on, and the inner solar system, outer solar system, then what kind of compositions we can expect, or what kind of differentiation, or what kind of geological processes might be there. And this is a very nice, or very meaningful plot that tells us the overall geology. For example, here is the Earth and the Moon. So it is represented by this blue circle here, the Earth and the Moon. So it share the same, let's say, special plot here. So by the way, this is the triple oxygen isotope, oxygen 18 to oxygen 16, and then the oxygen 17 to oxygen 16. And these plot whatever these, for example, Earth Moon line and Mars line is here, and then this different type of CI, LL, HL, and so on. These are different types of meteorites, and these meteorites are actually compared with the isotopes observations for Mars and so on, and then they found it, or classified that, okay, this kind of meteorite, for example SNC, this belong to Mars, and then this V-type, for example, this belong to Vesta, asteroid Vesta, and so on. So it represents how the isotopic composition or the chemical composition can be referred to the spectral observations. And one of the very important takeaway when we want to talk about early solar system is that these plots where it starts with C, V, C, O, C, M, C, I, and so on. So it means it's a carbon-rich kind of meteorites, and they are given the name C-type or so-called chondritic type. It represents, this is actually an image or photograph from asteroid series, and then showing what kind of internal or subsurface structure may be there. Yeah, and so I'm just going through very quickly the different types of these main classes are actually covered. C-type, it is covered by this down mission. Before that, very quickly, when I say meteorites, so chondrite, echondrite, stony iron, and iron. These are the broad four, we can say, broad types of classifications. And when we say chondrite, it means undifferentiated or maybe partly differentiated. And when I say differentiated, so it's the body has gone melting, and then whatever the mineral assemblages or the chemical assemblages have been actually have been arranged in such a way that in that given temperature and pressure, they form those so-called compatible minerals and then rock types, and accordingly, but these undifferentiated or partly differentiated means they have not gone through the stage of melting, and then they are representing more or less the undeformed nature, though there are actually so many so-called temperature and hydration reaction kind of processes. And then echondrite, so echondrite means they have been melted, all these echondrite, stony iron, and iron. So these we can say that these are actually the melted ones, and accordingly this differentiation means these different chemical assemblages are actually filtered out in terms of their density or the physical properties, and then they have gravitationally bounded to different compartments, and then they form different layerings. So so that's how these echondrites represent crust to the mantle, and then this stony iron represents the mantle core kind of sample, and then these iron meteorites represent the core of the so-called differentiated objects, including for Earth. And that's why meteorites are considered a very important marker to understand the planetary, including Earth, interior studies. So this is an overview because when I was trying to propose this asteroid mission, obviously I have to present the review of what kind of explorations have been done so far in terms of the flyby or orbiter or lander or rover and sample return and so on. And that's how it is showing different perspectives. These are actually for the comets, and that these are for the asteroids. So mainly I'm coming to the asteroids. Yeah, so different types, just to quickly go through. This is the C-type asteroid. So C-type asteroid, different C-type asteroids are actually have been explored. And then M-type asteroids, M-type means metallic type of asteroids. So if we look here, for example, the Psyche object, and the name of the asteroid Psyche, and the mission is also called the Psyche mission. And so the surface chemical property is representing this metallic nature, and it's also going to be a very wonderful exploration. Then we have B-type, so it is also covered by this down mission, and as I said, from 1970, this 1970 paper, how the spectral composition from meteorite and an observation were actually compared, and it was actually suggested by that time, and then such an advancement by that time in 1970. And then this one, S-type of asteroids, this is from Japanese mission, and then this E-type asteroid. So in this global context, what kind of, let's say, missions in the near future or still going on. For example, this Lucy mission, this is in the Jupiter, in the Jupiter orbit. There are also two this so-called small body or asteroid families, and then this is going to explore for the first time. And if I remember correctly, it has already started the flyby, or let's say the explorations. And then this DART mission, and this is also en route, and if I remember correctly, 2026, or they have also started the this one. And I think Tamuragu also somehow, I think he's also involved in some of the activities, and then this one from the United Arab Emirates, but I think there is no such information in detail. And China, they are also planning, but yeah, that mission details are also not available. And when we talk about asteroids, there are some kind of some type of asteroids that are actually considered in between asteroids and comets. So this is one of the examples, and this is, I think, the target of this Chinese mission, the potential mission. And then from this the asteroid series, so many, I'm showing this because when this mission was there, so many discoveries, one after another. And if India wants to be a mission for an asteroid, then my idea is that we should go to one of the large asteroids that would give us the opportunity or the window to have to make multiple or many discoveries. So in that regard, I'm just showing in, and this asteroid series has given lots of importance, and it has been compared with different exoplanetary kind of bodies, and then also with different Jupiters and the Saturn's moons. And in that regard, it is actually considered a very important one. And when we talk about this ocean world, it is actually very rare in the inner solar system when we talk about asteroids, because most of the ocean worlds, or when we say ocean world, it refers to a kind of an object that might have formed with underwater kind of concept, subsurface hydrous kind of layering, or the that kind of geochemical processes in its geologic history. So the reason for showing this kind of potential missions is that when India wants to have a kind of asteroid mission, the targets like Ceres gives lots of opportunities, and that is in the already kind of scientific concept that can bridge to the outer solar system. That is what I want to mean here. And then this is actually the target that I'm proposing. So this 10 Hygiea, the fourth largest asteroid, and you can see this is around 2.78 to 3.9 AU and highly eccentric, and then yeah, the properties and so on. And this kind of a density, 1.94 kg per meter cube, it tells us that this is actually very similar to this asteroid series. And this is a very new paper in 2020. And because of this paper, these authors suggested that this is a second dwarf planet in the inner solar system series, and that also tells us the importance. And the scientific importance here, the spectral feature comparing with asteroid series and Hygiea, and then this is just similar to this one. And the scientific importance is this plot. This plot tells us the heliocentric distance from the sun, and then the diameter scale, and the different types of let's say the asteroids. And as we go here accretion time means the time where this objects formed, and here this is based on the 3 micrometer feature or the spectral features, and depending on the nature of these so-called this kind of spectral features, here they have classified, for example, series like Europa, like, and then sharp one, rounded, and so on, featureless, and so on. And in terms of the physical and the chemical processes or properties, it tells us that in this time, in this special window, then it's a melted one, while in this window, or so-called in this heliocentric distance, and with this given accretion time, then these objects are actually kind of a transition to so-called the water ice. Here is ice melted, and then beyond this then is unaltered, or that ice melting is actually not favorable, and kind of icy nature. So these plot tells lots of the important physical and chemical properties. So with this, so the idea is that we should actually yeah, go to this Hygiea, and then this is actually one of the fantastic opportunities, and this is primitive and water and organic rich asteroid, and then that will give us lots of room for discussion, and how it is important in terms of scientific, what kind of science questions, and then so on. So I'm not going into these details again. So and when we want to propose a mission, then then I compile the potential payload, and the idea is that, okay, we can also have a lander after having let's say 50% of orbital life, and so on. And these are actually based on the review of the asteroid or planetary missions, and then the feasibility to develop, or already many of the payloads are flown on Chandrayaan-1 and then Mars and so on. So, and then when I was proposing this, so also took little time with my students, the feasible time windows, and in this regard I also talked to Tamoragu, but not in much detail, because this kind of work is actually very from the very scratch. So a very detailed study has to be done, what kind of time window is feasible, and then so on. So from the so if a very detailed analysis has to be done, and then for example we we refer to one of the papers, this Teller et al., and then I am actually not good in this kind of calculations, but as I said, with my 2 students, we actually try to simulate if we launch, for example, in 2028, means by 2024, 23, and then by window of 2028 with this 3 burn, 2 burn, means some of the parameters we don't have, and then we just simply assume those parameters, and then also we contacted the URAC team in Bangalore, and then they also provided some of the instrument, some of the details. I think that was in 2022. So I'm still considering this kind of opportunities, and then and since I'm actually in Department of Atomic Energy, I'm also considering a request and a visit to BARC, because they have in terms of this foil, there are some technologies that can actually be feasible for longer the mission time, and that kind of developments. I think even it's not with the existing Indian missions. Yeah, with this, I think This is actually my last slide. This is for the Apollo 11, and the message here. The astronauts were given a world tour, and so this is actually from a news clip in Azad Maidan, and then yeah, so how they are greeted, and how those were reported, and then yeah, and then this is the message, or that is this one: we came in peace for all mankind. And then this is actually in the base of the lander. And so with this, whatever, yeah, the scientific explorations, this is yeah, supposed to be for the mankind and then for the future. Yeah, and looking forward. And then once again, I'm very thankful to for giving this opportunity.